Now moving to another topic, polar and non-polar molecules. We saw that the polarity of the covalent bond rises when the difference in the electronegativity of bonded atoms is larger than 0.5 and less than 1.9. The polarity of the covalent bond is measured by a vector quantity called a bond dipole moment. The bond dipole is modeled as delta plus and delta minus, with a distance d between the partial charges. The bond dipole moment is equal to the product of the charge by the distance between the two atoms. The bond dipole moment unit is Dipole, which is coulomb by meter. Let's look at these values of the bond dipole of some covalent bonds. You can see that the bond dipole of some covalent bonds are higher than the other covalent bonds. For example, the bond dipole of carbon chloride is equal to 1.5 dBs. It is higher than the bond dipole of hydrogen carbon, which is about 0.3 dBs only. Another thing, you can see that the number of bonds increases the bond dipole value. For example, the bond dipole of carbon-oxygen, which is doubly bonded, is equal to 2.3 dBs, which is higher than the singly carbon-oxygen bonded together, which has only 0.7 dBs. We can predict the polarity of polyatomic molecules by combining the polarity of a bond and the molecular geometry of the compound. Sometimes molecules contain polar bonds, but they are not polar because the net bond dipole of the molecule is equal to 0. The net bond dipole of the covalent bonds of the whole molecule cancels each other. For example, for the linear carbon dioxide, you can see two oxygen atoms doubly bonded to a central carbon atom. The bond dipole of carbon-oxygen doubly bonded together on the left is equal to 2.3 dBs, with a vector pointing to the left. On the other hand, the doubly bonded carbon-oxygen on the right pulls towards the opposite direction, with an opposite vector and the same value, 2.3 dBs as well. Remember the direction of the arrow towards the more electronegative atom. So, the net dipole moment, the molecular dipole of the carbon dioxide, is equal to 0. The bond dipole pointing to the right, 2.3, cancels the bond dipole pointing to the left, which is 2.3 dBs as well. Although carbon dioxide has polar bonds, carbon dioxide is a non-polar compound. Another example, if you looked at the geometry of boron trifluoride molecule, you can see that the three boron fluoride bonds are pulling in opposite directions to each other. So their bond dipoles are cancelling each other with a net dipole moment equal to 0. The same happens with carbon tetrachloride, which has 4 carbon chloride bonds pointing to opposite directions to each other, cancelling each other bond dipole, giving a net of 0 dipole moment. You could see that the three compounds contain polar bonds, carbon-oxygen bonds, boron chloride bonds, and the carbon chloride bonds. But the net dipole, the molecular dipole of each molecule, is equal to 0. This is how compounds contain polar bonds end up being non-polar compounds. Let's look at water molecule. We all know that water molecule is a polar compound. Let's try to specify the direction of the molecular dipole moment. On the left, the two hydrogen atoms are connected to the oxygen atom. The two bond dipoles of the two covalent hydrogen-oxygen have dipole vector direction coming from the hydrogen towards the more electronegative oxygen atom. The two bond dipoles add up to each other. Each hydrogen-oxygen bond has a bond dipole equal to 1.5 and the two bond dipoles are equal to 1.85 dBs. You can see that the red area represents the electron density, which is concentrated over the oxygen atom.